In this lab, we are observing Newton's second law of motion. So Newton's second law of motion says that an object at rest will stay at rest and an object in motion will stay at motion at constant velocity. This can be described by the equation, the net force is equal to the mass times the acceleration. So an object at rest will stay at rest when there is no net force, so there's no acceleration. As well, when an object is in motion, the forces cancel out, so there's no acceleration and the object stays at constant velocity. So here we have the force of the push minus the force of the friction, which we'll see in a minute. So we see this in two cases, an observed model and a predicted model. So for our observed model, we see the ball, which is given a push and friction's acting against it, and they cancel out to equal net force is 0. So the object stays in motion at a constant velocity. Now we have to put this in tracker to observe the movements of the ball. So we put our axis in the middle of the ball here with positive y going to the right and positive x going to the right and positive y going up. Now if the axis were reversed, then simply our velocity would be negative, but it would still be the same magnitude. So we see here, running the object in tracker, it records the position of the ball as it moves through time and gives us a table with our movements and a graph of the position versus the time. Now we have our predicted model. So to get our predicted model, we need to get a few measurements. So we take the initial time, which is 0 seconds, and the initial position, which is 0.001 meters. As well, we want to get the final time from the table, which is 0.767 seconds. One more measurement we want to get from the table, which is the initial velocity of the ball. So we did the change in the displacement over the change in time. So we take our second measurement minus our first measurement over the change in time, and we get 0.3702 meters per second for our initial velocity. So now we change our code. We need to get the mass of the ball. This is in kilograms, and simply we just measure the mass. We also need to change the initial position of the ball. So as I said before, the initial position is 0.001 meters. So we insert that into the y coordinate of our position vector. And the velocity is 0.3702 meters per second. So we put that in the y coordinate of our velocity vector. And this is all at time is 0. Now, we have a final time from our tracker, so we want to run through the loop getting the updated velocity and position up until the time 0.767 seconds. Now we must edit this line here. The net force is 0. That is what it is showing in Newton's second law of motion. So we need to make sure the vector is 0. As well, we have to update the velocity of the ball, which is velocity initial plus acceleration times change in time. And we know the acceleration is equal to the net force divided by the mass as described by Newton's second law of motion. Additionally, we need to update the velocity, the position of the ball, which is the initial position plus the velocity times the change in time. Now, we run our code through, and we get here the ball moving along the x-axis as we observed. Here we have a graph of position versus time and velocity versus time, which is constant. And then our values are printed out below. Now we can compare the two. So we have our predicted position in blue and our observed position in orange, and we can see that they essentially are the same line, and that shows that we have a constant velocity. There are some slight differences, and that is due to the camera. There's a slight change in the y, and it wasn't exactly perfect. So we have some slight variations, but you can see that our observed position and our predicted position show that the object in motion will stay in motion at constant velocity unless acted upon by another force.